Okay, you can see your presentation. You can start. Thank you.
Okay, thank you very much. Good afternoon, everyone. I will present our work, experimental and numerical strength of pervious concretes here. Um, well, yes. The the problem that we have is that in Brazil we have some problems this year with the expressive increase of the runoff, and we have a lot of flooding. Then it is a actual problem that we have here. Yeah, I think that in other parts of the world it's increasing also. Then we see that a variable alternative to mitigate these issues, the use of pervious concrete as a mechanism to design and restore the soil infiltration capacity. This pervious concrete is composed by a porous structure formed by a coarser aggregate and a small layer of cement paste. The pores are non-uniform distributed along the material. This characteristic, the high amount of voids, significantly reduce the material's mechanical strength. Well, we use a mixture that was prepared here in Brazil with a aggregate cement ratio of 4:1 and a water cement ratio to 0.26. We use an additive with 0.07 of ratio of cement. The concrete that we do has a porous target of 25%, and we use a Brazilian EPT method to do the mixture. The material that we use a material of our city, of our region, that the stone is as basaltic origin, and it has a nominal diameter of 9.5 millimeters. We use a cement Portland, a kind of Brazilian cement Portland that is more next to the international one, and we use a V-mark additive to improve the rheology of the concrete. Yes, this here is the aggregate particles that we have in our concrete. Well, the casting and compacting, we define a density that we need to have in the concrete, and we calculate the weight that that our specimen must be, and we put all the material in the molds. Then we compact them and verify the weight. If we have the exactly weight that we are expected, this specimen is okay. If not, we complete and check again the process. We always control the density of the specimens to have the exactly mass in every specimen. The compaction was carried out in a single layer using a roller to simulate the in situ compact methodology. The samples were molded after 72 hours and cured 28 days in a wet chamber. After that, we yes. After that, the mold that we have, we are cubes, blocks, a block, and a prism to do the specimens, to do the test. Sorry. Here, here. This is the infiltration rate. We can see that this material has an infiltration rate of 1800 thousandths millimeters by hours. Then is a good pervious concrete in this issue. Well, the compressive strength, we do the mechanical characterization, compressive strengths, splitting tensile strengths, and the flexural strengths, 3 points and 4 points of flexural test. We found experimentally these values. We can see that the compressive strength is relatively small, but it's a very porous material. Uh, all the properties that we find experimentally, we will use to the simulation of this material. For the simulations, we utilize the lattice discrete element method. This method is based to represent a solid by a 3D lattice. The lattice is based is formed by a repetition of a basic cubic moduli like this that is repeated in the in three directions. This basic moduli has 20 elements and 9 nodes. Every node has 3 degrees of freedom in the direction of the displacements. Uh, we calculate the area of of every one of these elements to can represent exactly the elastic properties of the solid that we represent. This is the discrete strategy of the representation of the model. Then the time discretization is due by the equation of motions, where M is the matrix, mass matrix, and C is the damping matrix. Uh, these two matrices are diagonal. Then this equation are no coupled. F are the internal forces that are related with the displacement of every element of the model. The relation by a solid is this is a cubic solid that is cut in 2 parts. Then the energy release in this act is must be the same that the energy release when we cut a basic cubic moduli. Then we calculate where is the fracture area needed to have exactly the same energy in the two cases. This fracture area is utilized also in the element. Then every element has 2 areas, one area related to the fracture and another area related to the elastic properties. Every element has also a bilinear constitutive law when this the area inside of the constitutive law is related to the fracture area of the element. We put this method, this discretization, in the abacus to use the abacus properties of the program, and we represent the 3D lattice as a truth, a lattice of 3D truth finite element methods with 2 nodes. We use the T3, D2 elements. And for represent the bilinear constitutive model, we use a combination of the linear elastic behavior plus the numerical model that also use the fracture energy as a property. Is very similar to that we use. Then we utilizing this model, we do the 4 tests that we do experimentally. Then here is the 3-point bending flexor test, the 4-point flexor bending test, the compressive splitting tensile test, and the compression one. All these the simulations were done in 3D, and we use the properties of the materials as our random fields. Then we have 4 simulation of every kind of test. Well, the result of the compressive test is we do this 4 simulations, font and compressive strength of 478 as a mean value, and this is yeah, and this is are the failure configuration when the black elements are the broken ones and the gray are the non-broken. And here we can see that our configuration is very similar to the found experimentally. Also, the value of the mean value of the simulation as the experimental results are very, very similar. This is because we use this test to calibrate the model. With always using the properties of the elastic properties and the fracture properties that we found in the experimentals. The other simulation is the split intensity strength. We found a medium value of 0.63 MPa, and in the experimental is a little bigger value. But the failure configuration is very similar. Always we have a crack very similar to the experimental one. In this case, is easy to result. The 3 point flexural strengths. We also here also the 4 simulations, and our mean value is 2 MPa, and the experimental one was 178. We have here a little more expressive error, but the crack propagation, the crack failure also is similar that we found in the experimentals. The last simulation was the 4 point flexural strength. Here are our 4 simulations, and the mean value that we found on the strength is 184. These are two of our experimental results, and the error here is a little less. One interesting thing is this last test was the one what we used to calculate the elastic modulus in the experimental campaign, and these are the load displacement curve found experimentally. These are the 4 results, and here are our numerical results. Here we can see that our value is very similar of the strength, but the failure configuration, sorry, but the post-peak part of the curve is not equal. We have a fragile break, and the experimentals that we can find this failure break. Then we need to improve now the post-peak curve simulations. We need here increase maybe the fracture energy that we use to represent the model. Well, the conclusion of the work that I'm presenting here is that the compressed strength of pervious concrete is acceptable, but uh, we need to improve this material to use in other places that not only for civil walkings or something like this. This material is suitable for pedestrian walkways, but we need to change. We need to increase the fractal the fractural test, increase the value to have uh, the possibility to utilize in light traffic cases. Um, the utilizing the material properties that we found experimentally, we have good results with the LDM simulations, principally by the strengths that we find and the failure configurations. The cracked parts then are very similar with the experimental ones. We need now to work to capture very well the post-peak behavior of the 4 point flexural test that we have problems for now. Well, this is the work that we are doing for now. Thank you very much for your attention. This is the group that we are working here in Brazil. Thank you very much.